Hi, thank you so much. So today we'll be discussing HDTN, which stands for High Rate Delay Tolerant Networking, which is a groundbreaking software solution developed by NASA to address the unique challenges of space communications. So before diving into HDTN itself, let's understand the problem we're solving. Space naturally exhibits several significant communications challenges that differ from terrestrial networks. First, we deal with disconnection, meaning an end-to-end path isn't always available between communicating parties. Second, there's disruption, where free space links are frequently interrupted due to orbital mechanics, weather, or other factors. And third, delay. The vast distances involved in space negate traditional acknowledgement-based protocols like TCP. Our goals for planetary networks are threefold. First, we reduce mission burden with short mesh links for increased connectivity, which enables proximity telerobotics. Second, we adopt a common architecture to reduce development costs across missions. And third, we enable reuse of hardware and software across different environments, whether that's Earth orbit, lunar operations, or deep space missions. And this aligns with NASA's space communication and navigation architectures, which are migrating toward greater flexibility, scalability, and affordability. HDTN was created to optimize DTN network protocols over high-rate laser communication links. The team has collaborated for several years with members from Johnson Space Center, Goddard Space Flight Center, and Marshall Space Flight Center to demonstrate DTN capabilities over gigabit per second optical links as part of the Laser Communications Relay demonstration using the Integrated Laser Communications Relay Demonstration Low Earth Orbit User Modem and Amplifier Terminal known as Illuma-T, which was demonstrated on board the ISS. Early trade studies showed that previous networking implementations would inhibit the full use of the high rate bandwidth. So HDTN was designed to implement DTN store and forward and data transmission capabilities as fast as possible while maintaining the processing and memory constraints of a flight environment. This diagram illustrates a complex multi-hop network that we successfully tested involving the International Space Station in low Earth orbit, the Laser Communications Relay demonstration in geosynchronous orbit, and ground stations in Hawaii, California, New Mexico, and Ohio, plus a PC-12 research aircraft. The experiment objectives were comprehensive. We streamed video data across multiple independent networks, emulated several mission concepts of operations with induced latencies, and baseline performance across different network configurations. We tested various protocol combinations, including TCP, STCP, and LTP, both with and without data custody transfer. We demonstrated adaptive 4K HD video streaming at varying resolutions and data rates, implemented security features, including encryption and authentication, and successfully handled handoffs and outages. The data rates achieved were impressive, with downlink rates reaching over 900 megabits per second. HDTN implements a comprehensive suite of delay-tolerant networking protocols that form the DTN protocol stack, standardized by organizations such as Consultative Committee for Space Data Systems, or CCSDS, and utilized by NASA's LunaNet interoperability specification. This slide shows how DTN sits as an overlay network layer, providing reliability and store and forward capabilities above the convergence layer, which interfaces with varying underlying transport and link protocols. The benefit of this architecture is its flexibility, as it can work over virtually any underlying networking technology, from laser communications to RF links to traditional TCP IP links. So here are some of the highlights of HDTN's key functionality. HDTN provides high-speed data transfer capabilities, enabling the throughput needed for modern space missions. It includes store and forward capability, which is essential for delay tolerant networking, where data can be stored when a link is unavailable and forwarded when connectivity is restored. HDTN provides reliable transport mechanisms to ensure data integrity across unreliable space links. The system supports multi-hop routing, allowing data to traverse multiple relay points on its way to its destination. Security features are built in, providing the encryption and authentication needed for mission-critical communications. One impressive capability is 4K video streaming, needed for high-definition video transmission across space networks. HDTN provides a comprehensive application programming interface for integration with user applications and includes a graphical interface with trending and logging capabilities for operations and monitoring. And we also maintain compliance with protocol standards, ensuring interoperability with other DTN implementations. So these are just some of the achievements of the project. Overall, we've completed 6 new technology reports and 4 NASA open source software releases. We also spent a significant effort reaching NASA procedural requirements 7150 Class B compliance. So we are able to meet software engineering requirements for large-scale space robotic missions. And as part of that effort, we completed 26 software documents totaling close to 2,000 pages, and we publicly released many of the documents for any of the users who want to adopt the software. The team has over 39 conference papers and journal articles, and we host a website with all of our publications, as well as external publications that we have found of others using HDTN, as well as information about the project, including links to YouTube videos that the team created with tutorials on how to build HDTN on different platforms. We received a NASA Group Achievement Award, won an R&D 100 award, and received a NASA Software of the Year honorable mention. And additionally, we've completed 2 spaceflight demonstrations, the ISS Illumity test campaign from March to June of 2024, and the TechEdSat 11 CubeSat demonstration from July of 2024 to February of 2025. At its core, HDTN implements a comprehensive suite of space networking protocols. It's fully open sourced and available via NASA's GitHub repository, making it accessible to anyone who wants to use or contribute to it. The software is built with modern dependencies and follows contemporary coding standards, making it maintainable and extensible for years to come. And this slide has a few screenshots of the HDTN web interface that is used for troubleshooting and monitoring. And on this chart, this is actually a video with audio, so I'm going to play it. So tell me if you can't hear it, and if not, we do have our PI, Daniel Rabel, who created the video, so if it doesn't play, he might be able to narrate it. So just let us know if you don't hear the sound.
In order to test our HDTN software in the field, we deployed it across a large-scale aerospace network by launching it to the International Space Station, installing it at several ground facilities and intermediate nodes across the country, including a cloud-based implementation through Amazon's Web Service, and lastly deployed the system on our research aircraft. Together, this infrastructure would provide a robust and non-deterministic environment to evaluate HDTN's capabilities across real laser, RF, and terrestrial links. We began evaluating the technology in the laboratory to ensure our applications such as 4K ultra-high definition video streaming were configured for optimal performance in the field. Next, we integrated HDTN with the avionics systems to deploy it throughout the network. By coordinating with operators of the laser communications relay demonstration, we would receive daily updates of opportunity when their spacecraft would connect the ISS to the ground network. During these periods, we would deploy our aircraft, also equipped with HDTN and laser communications, to provide an end-to-end data path with the ISS. Often, the local weather provided suboptimal conditions, which presented an opportunity for HDTN to exercise its store and forward capabilities as the laser links would fade in and out. During these flight tests, we performed large and small file transfers between the aircraft and the ISS, both with and without custody transfer. We streamed live 4K video from our onboard camera, exchanged HD videos with space, most notably pet videos, and did so while employing network security, including integrity checks and confidentiality at rates nearing 1 gigabit per second. In addition, all of the network operators were able to gain experience configuring HDTN and taking advantage of its easy-to-use web interfaces and data logging. Through subsequent flights, we were able to evaluate additional capabilities such as chat applications, serverless email services, avionics clock synchronization, and crew biometric monitoring, all enabled by HDTN. Overall, this successful experimental campaign raised the technology readiness level of HDTN to operationally serve human and robotic missions for Artemis and beyond. In order to test our
Okay. So, as was kind of noted in the video, HDTN has achieved the highest rate DTN data transfer in space, representing the first use of modern DTN protocols on the ISS, including Bundle Protocol version 7 and Bundle Protocol Security. We've completed the first spaceflight test of Bundle Protocol Security with high rate secure streaming demonstrated on ISS. HDTN has been integrated with advanced communications technologies, including user-initiated services, cognitive and AI optimizations, and 3GPP mobile networks. We've improved the user experience significantly, and the open source nature of HDTN provides opportunities for collaboration with support from everything from embedded systems up to high performance computers. And our GitHub repository has received over 61,000 views, demonstrating significant interest from the community. HDTN has advanced the state of the art towards a future interplanetary internet. We've demonstrated record-breaking data rates, including reaching 1 gigabit per second in a space environment and 30 gigabits per second in a laboratory environment. We include advanced features such as multiple DTN-enabled applications, application programming interface, web interface, security, and routing, and have been integrated into commercial cloud networks. We've also demonstrated automated scheduling in our CubeSat experiment. We're unaware of a similar space networking framework that includes as many advanced features at the maturity level of HDTN, including multiple flights demonstrations and meeting NPR 7150 Class B compliance, making it a mature product that is ready for mission use. This is a little bit about the HDTN development timeline. It's been evolving as a product for over 10 years. Early concepts started as a white paper with recommendations on how to implement DTN for high-speed communication. We completed a flight test of early portions of the encoding and decoding library in 2019 and went on to complete our initial open source release in 2020. Since then, HDTN has developed many more features, increased its robustness, and continued to advance its TRL level. During the research and formulation phase from 2009 to 2014, we analyzed problems associated with high-rate space networking, established the concept of operations, and proved feasibility of separate control and data planes. We identified critical components including scheduling, storage, routing, security, and streaming, contributed to international open standards communities, and prototyped and demonstrated a performance optimized architecture in a laboratory environment, achieving TRL 2 to 3. During the technology development and testing phase from 2015 to 2022, involved the implementation and documentation of the reference design. We established a space networking emulation laboratory at Glenn Research Center and also integrated testing at JSC's Software Development and Integration Laboratory. And we performed field testing with GRC aircraft laser communications and publicly released our products on GitHub, achieving a TRL 4 to 6. Flight technology demonstrations during 2023 to 2024 included the laser communications relay demonstration and demonstrated the software in a relevant environment. We achieved compliance with NPR 7150.2D engineering requirements, reaching a TRL of 7 to 8. The main HDTN components include ingress, egress, storage, router, and command and telemetry interface. Its highly modular architecture is event-driven with a library-oriented design. Some library components, such as the LTP library, have been used by other teams, and several teams have created their own modules for HDTN, demonstrating the extensibility of the design. The architecture of HDTN was designed with both performance and usability in mind. From a performance perspective, we use a message bus architecture that allows for both distributed and single process deployment modes, and the design avoids semaphores and mutex locks on shared memory, which is a critical optimization for high-speed operations. We also avoid unnecessary memory copying and leverage asynchronous operations throughout. And on the usability side, HDTN is platform independent. It's built on well-maintained dependencies and is fully open source with comprehensive documentation. We provide a graphical interface for ease of use, as well as both an API and command line interface for different operational needs and integration scenarios. One of the greatest strengths is its broad platform support. For single board computers, we support Raspberry Pi, Cesium Astro SDR, Portentia X8, and Jetson Orin platforms. We also support containerized deployments, including Docker, Kubernetes, and AWS EC2. And we've also integrated HDTN with simulation and emulation platforms, including OmNet++, Core, and Exada. For operating systems, we support multiple Linux distributions, including Ubuntu, Debian, Oracle Linux, and Ubuntu on ARM64. Windows 11 64-bit is also supported, as well as Mac OS on both Apple Silicon M2 and Intel x64 running Sonoma. And we've verified operation on FreeBSD, OpenBSD, and Raspbian. This broad platform support ensures HDTN can be deployed in virtually any environment needed by our users. HDTN has followed an evolutionary life cycle with many capability improvements. We've completed multiple early trade studies to evaluate existing DTN implementations and determined important design decisions, needed features, and conducted interoperability testing to ensure compatibility with flight and ground software commonly used in space networks. The system is highly modular and event-driven, following a library-oriented design philosophy. These libraries have been reused by other projects, demonstrating the value of a modular approach. And perhaps most importantly for technology transfer, external users can add or replace components to customize HDTN for their specific needs without having to rewrite the entire system. Our team strives for technical excellence in our software engineering process. Our requirements development and traceability process uses model-based systems engineering and automated report generation. We use a continuous integration and continuous delivery pipeline for automated builds, unit testing, static analysis, and integrated test. And the team developed an automated test framework for requirements verification that can create and modify network packets. This software is extensible to other implementations and has also been made publicly available. So you can find the automated test framework at github.com/NASA/DTN test framework. And this commitment to software engineering best practices ensures HDTN is not just high performing, but also reliable, maintainable, and suitable for mission critical applications. HDTN comes with comprehensive software documentation covering every aspect of the system, from requirements and architecture to the user guide and API references. Our 26 software documents include software requirements, user guide, version description document, data dictionary, and design documents, which have all been made publicly available. This documentation is essential for technology transfer as it allows new users to understand and deploy and integrate HDTN. HDTN has been adopted across multiple use cases beyond its original space communications purpose. In cognitive networks and automation, and particularly mobile networks, HDTN is being used as a network overlay by companies developing prototypes of lunar surface networks based on 3GPP standards, including 5G technology. In aeronautics, HDTN was utilized in optical communication experiments tested on a research aircraft in 3 separate occasions in 2019, 2021, and 2024. And these tests demonstrated HDTN's viability for airborne applications. For network emulation, HDTN has been integrated into multiple network emulation tools and test beds used by industry, academia, and government agencies. And this makes HDTN valuable not just for operational systems, but also for research and development environments where network scenarios can be simulated and tested. We have several resources available for anyone interested in using HDTN. Our project website provides overview information and context about the project. In the NASA software catalog, you can find HDTN listed with the official catalog entry and release information. And on GitHub, we maintain 2 repositories, the HDTN main repository, which contains HDTN itself, and also the DTN test framework, which contains the testing framework. And we also have a YouTube playlist with tutorial videos. So here's our outstanding HDTN team that has made the project possible. HDTN has radically improved DTN software performance and user experience. It has been adopted by multiple users across different domains and infused into real operational networks. All of our documents and software are publicly available and free to use. And we encourage anyone interested in delay tolerant networking, space communications, or advanced networking research to explore HDTN and consider it for their applications. And I can go through briefly and show the links if you're interested. So here is our main website. It has some events, an overview of the project, some videos, and this is the tutorial series that has a variety of different topics. And then we have links to our software documentation. And then there's also 10 years of publications by the project on a host of DTN related topics. And here is the software catalog entry. So this is the HDTN version 2.0 network operations release. And this has a little bit about the different features that are included. And it also links to the main GitHub, NASA HDTN. And here we have the code, and we also have a short overview, and then a little getting started page with information on building on different platforms and some of the features available. And if you go up to the top also, you can click on releases here. And so this is the tagged release that we have for every major version. And the nice thing about this is that it has links to the software requirement specification, the software test report, the version description document, and the user guide, all for this tagged version of HDTN version 2.0. And then finally, we have the test framework is also available on GitHub. And so this is the framework that was actually used to generate this test report. So you could kind of go back through and see the requirements in the test report. And then if you're interested in your own tests, we have it available. And we also have here, if you go to releases similarly, you can get the test framework, software requirements, and the design and the version description. And so I think that's all I have. I can take questions.
Oh, thank you. That was a very insightful presentation, and I enjoyed the video demo a lot too. We did receive a couple questions via email. Let me go ahead and start with the one in the chat. What protocol was used for the file transfers in the demo video?
We have a couple different, so HDTN has its own file transfer tool that basically it's just a little tool that you can take a file, put it into a directory, and then it'll automatically break it up into, and one thing I didn't talk too much about is like for DTN and the protocol unit is called bundles. So that's what we're sending kind of as packets. So it will just automatically take it and convert it into bundles. And then we have another little receiver application. So that's the one I think that we mainly used was our HDTN file tool, but it's
I see.
basically bundle protocol.
Okay, great. Thank you. And then let's see. Are there any? Well, I see that Daniel already responded to some of these, but I'll read a couple more here. Are there any flight software integrations or example integrations that are also public?
We do have a tool that is a packet, send packet and receive packet, and that was used to integrate with F prime. And it's also can be used to integrate with any number of software. It just basically takes the bundle and can put it into a buffer. And so then you can integrate really with any software.
Got it. Okay. Thank you for that. Um, is there a requirement for LunaNet providers to also support HDTN, or are both architecture completely disjointed?
So LunaNet uses the CCSDS specifications, and HDTN took those specifications and made them into software requirements. So it's really, we're implementing the protocols based on the specification, and LunaNet only calls out the protocol specification.
Got it. Okay. I see a comment in the chat that said, this presentation just made the rest of the presentations make sense. Great presentation. And can you talk a little bit to what extent you ran HDTN on the CCM Astro SDR 1001, or what kinds of experiments that SDR supported?
So we have, and if you go to that project page and look up, there's actually a paper on it on a test bed that was used on another project that used the cesium Astro SDR to emulate a user spacecraft. And then we have a high fidelity test bed that emulates the RF link. So it was used as that as part of a demonstrating how you can switch between commercial and NASA relays in a high fidelity RF testbed.
Okay, thank you. I received a couple more general questions via email, so I'll read those. And if anybody else has any more, feel free to keep typing in the chat. What's the biggest misconception teams have about HDTN when they first evaluate it, and what usually clicks for them after hands-on testing?
Hmm. I don't know. That's a tough one. Do you
It's a
have
tough
any
one.
ideas, Daniel? I've been talking to see if Dan has any ideas.
It's a more abstract question.
Yeah, maybe I'll try. I think with DTN in general, because a lot of it has been more researchy, I think new users expect that they need to have some formal background in space networking to make DTNs work. And what we consistently hear from users is that, and this is, credit to the development team putting together the graphical user interfaces and the logging and the online FAQs and tutorials, is that you don't need to know that. And there's a lot of power at your fingertips that's easy to configure, and a lot of the networking under the hood stuff has been abstracted away. And so ease of use was one of our goals in addition to performance. And I think we've happily heard that feedback over and over again, is that they kind of went into it expecting that they'd have to do more to get it up and running, and it's been anything but that, and they're able to get it up and going in the lab and on their systems much more quickly than they anticipated.
Okay, thank you. And we have another question in the chat. And you may have touched on this a bit. Have you encountered any issues with the synchronization?
Time synchronization?
I'm assuming this question from Mehdi Ramadi. Yes, time synchronization.
I think the only thing, and Dan might know on this too, is that, and this is just in all bundle protocol, is that you are using the computer clock as the time. And so there's a thing in which bundles will expire. So based on the time, which is coming from the computer clock. So um, that's one thing. You just have to make sure that you have that synced up if you're going across different computers or different time zones. But I don't think we really had it be an issue for us.
Got it. Okay. And how sensitive is HDTN performance to inaccuracies in contact plans, especially for missions with highly dynamic geometry?
So one thing that we do have, and actually on that test bed that we were mentioning with the cesium Astro, is we do have the contact plan, but HDTN can also detect, is depending on the protocol. Actually, we've modified it for different protocols, but in particular LTP, which would be the one that you're using over long distance links. We have a little our own modification to that where we know when the link is up and when it's down. So we can actually ignore the contact plan if you so desire, and just know to stop sending based on the status of the link. So that's actually how we did our testing on ISS. We just have one always on contact, and then the protocol itself is going to know when the link is up and able to send. So that's one way. And then we also have another way via the API where you can send updates in runtime to the contact plan. So we have some flexibility there both ways.
Okay, thank you. Um, Another question. I just have one or two more via email, so if anybody else wants to type a question in the chat, please go ahead. This we have a large university audience, so for universities and research labs exploring contact plan algorithms, what have you learned from implementing contact graph routing and contact multigraph routing with dynamic updates? Are there open research questions or benchmarking areas where you'd like to see the community contribute?
I know there's interest in regional routing where the traditional contact plan, you're saying that you have knowledge of the whole network, and then you have a contact plan and you have to try to distribute it. And that in itself is an issue. So I know there is some work proposed that says, well, you can break the network up into regions and it'll be smaller, and there will be some areas where you don't need to know. And that is actually how probably the real networks will be, is when you integrate with commercial partners, there's going to be areas of the network that you have really no control over. So running the contact plan and having all that information about it is going to be not possible or very difficult. So the regional routing or other things in which you don't have to have full knowledge of the network would be good to look into, or areas where you have this kind of black box network and you don't know what algorithm or what they're running, is going to be good for when we have commercial networks and different agencies that control the networks.
I see. Okay, thank you. And another question in the chat, both LTP and UDP could be used to converge too. Have you used both or just LTP? And are there any pros and cons?
We use both. And in fact, the way that we most commonly run LTP is it's over UDP. We also have an end cap layer, and that's kind of more space comm systems will often use NCAP in the case if you don't have actually an IP network stack. So yes, we've done them both and we have some variations on it.
Okay, thank you. So I have one more email question that we can close with, and if anybody else has any, keep typing in the chat. So this is a broader question, but if an enterprise ground network wants to integrate HDTN alongside existing DTN stacks and mission systems for typical onboarding with dependencies, API use, and operational tooling, how quickly can teams progress from evaluation to um, on orbit or field deployment? Just rough estimate.
It probably depends on the team. I mean, we've had a couple different agencies work with it and have gotten in a few weeks with some help from our developers. And I think it's even easier now than a few years ago because we spent a lot of work on the documentation. So there's a lot more available. I don't know, Dan, do you have any thoughts on that as well?
I think that sounds pretty accurate. I mean, when we get new folks within Glenn, interns are pretty much up and running with it within a few hours. By noon on their first day, right? They're running HDTN. So to set up and deploy, a network in the field, I would say, with a decent team, a few weeks sounds reasonable to me, based on the feedback that we've gotten from our partners and users.